Lab 5 falling slinky. In this lab, we will be predicting the motion of a fully stretched slinky dropped from height using Newton's second law, tension, gravitational principle, and drag force. First, we use Tracker to analyze the spring's motion from the video, and then we will try to predict the motion in a glow script model. Fundamental physics principles used in this lab were Newton's second law, so we can calculate the forces acting on the object, and from that, we also derived the positional update and the velocity update formulas, so we can, in the computational model, predict how the slinky is going to move. The force of drag, because there's drag when the slinky starts falling down to the ground, gravitational and tension formulas as well. Here's a brief preview of our results. Both our computational model and tracker model found that the bottom of the slinky will stay stationary until the top of the slinky reaches the bottom. The system for this experiment was the slinky, while the surroundings for this experiment was Earth, and the atmosphere, and everything but the slinky. Here are our initial conditions. The mass of the slinky was determined to be 0.204 grams. The length of the slinky was 1.75 meters. The initial velocity of the slinky was 0, and the initial position was 0.0034 for x, 0.034 for y, and 0 for z. Here's a brief look at what we did in Tracker. Here's our glow script code. In this portion, we set all the initial conditions I just mentioned to you in the previous slide. And we also set B, which is our constant used for the drag force. So this code is broken down into two while loops, one for the portion where the spring is catching up to itself, and then one for when the spring is actually falling to the ground. This is the part where the spring is catching up to itself. We first calculate net force. The only forces acting on this object are gravity and tension, which we calculate right here. Tension is just the positive of the force of gravity. Net force is those two combined, and then we use velocity and positional update to update the position and velocity of the ball, the spring. Here's the second part of our glow script code. This is when the spring is actually falling to the ground. So the forces acting on the object during this point are force of gravity going down and the force of drag going up. And then we calculate net force by adding those two together, and then we get the velocity update, and using the velocity from the velocity update, we calculate the position using the position update. So when we run this glow script code, we get this graph of position versus time. As you can see, up until 5.5 seconds, the bottom of the spring does not change position. It only changes position afterwards, because that's when the spring actually starts falling to the ground. If we then graph the tracker versus the computational model's results, we can see that they are both pretty similar. This graph represents the computational model as blue and the experimental as the tracker model as orange. Like I said before, from the comparison of the two experiments, we can see that in both experiments, the bottom of the slinky stays still until the top is caught up with the bottom. But remember, on the graph, the orange had deviations from the blue. This is because there's possible sources of error in like point placement during tracking. The camera was also tilted in the original video of the slinky being dropped, and there could have been unknown forces acting on the spring. Maybe there's wind, Quick discussion. Why does the bottom of the slinky not move? This is because the bottom of the slinky is being acted upon by not only gravity, but also tension from the upper part of the slinky. These forces are opposite in direction and equal to each other, so the net force comes out to be 0, and so the bottom of the spring does not end up moving. But what if we added a weight to the bottom of the slinky? Well, imagine the bottom of the slinky as a point. The weight would add an extra force going downward onto the slinky, and that would break the balance between tension and the force of gravity on the bottom of the slinky, making the slinky start falling downwards.